And there were no atoms because the temperature was too hot to have atoms. And the universe expands. As the universe expands, it cools. About 1 second after the Big Bang, roughly 1 second after the Big Bang, the universe gets cold enough. Suddenly, and this is a prediction of Big Bang cosmology, you have protons and electrons and neutrons. So a few milliseconds after the Big Bang, you have protons and neutrons. And roughly 1 second after the Big Bang, the temperature is low enough that a proton can capture the neutron and form a deuterium nucleus. So deuterium is heavy hydrogen. Normal hydrogen has a single proton. Deuterium has a proton and a neutron. So 1 second after the Big Bang, roughly, you can form the first slightly complicated atom, which is deuterium. Once you form deuterium, deuterium can very quickly capture another neutron and another one and form helium. Helium is famously known. Helium, the name helium comes from helios, which means the sun. The helium was found for the first time in the sun. And helium is, so what is happening over here is fusion. It's fusion of basic particles to produce bigger nuclei. Exactly what's happening in the sun today. So in the sun, you have hydrogen fusion, which produces helium and gives off a little bit of energy. Exactly the same process happened at very early times in the universe. Roughly 1 second to about 20 minutes after the Big Bang. The peak is about 3 minutes after the Big Bang. And so what's happening is that in the whole universe, you have deuterium forming, and then the deuterium very quickly forms helium. And a little bit of the helium, because helium is a stable element, a little bit of the helium forms lithium. And that's it. And then the universe continues to expand outwards. And so the process, so this period of roughly 1 second to 20 minutes after the Big Bang is called Big Bang nucleosynthesis. Because you are synthesizing nuclei, the nuclei of atoms. And the elements that you produce are deuterium, helium-3, stable helium, helium-4, and lithium. There are 4 elements that are produced in Big Bang nucleosynthesis. There's no carbon that's produced. There's no iron that's produced. Carbon, iron, zinc are all produced in stars. The only 4 elements which are produced in the Big Bang, after the Big Bang, are deuterium, helium-3, helium-4, and lithium. And that happens somewhere over here, this white period, about a few minutes after the Big Bang. Right? But remember, this is important. This is happening all over the universe, everywhere. This means that the amount of helium compared to the amount of hydrogen should be the same everywhere in the universe. The amount of deuterium compared to the amount of hydrogen should be the same everywhere in the universe. And that's a prediction of the Big Bang. The prediction is that wherever you look in different galaxies, the amount of helium and the amount of deuterium must be the same. It depends, the amount that you produce depends only on density. Because the density, the higher the density, the more helium you produce, typically. So the amount of helium, deuterium that you produce, everywhere in the universe depends only on density. And you'll see that in a little bit. So that's a complete prediction of the Big Bang. Wherever you look in the universe, there should be the same amount of helium compared to hydrogen. Wherever you look in the universe, there must be the same amount of deuterium compared to hydrogen. That happens over here. So now the universe expands, keeps expanding outwards, gets cooler and cooler and cooler. And now you have a problem, because the universe contains definitely protons, electrons, neutrons, helium nuclei, and radiation, electromagnetic radiation. But now you have a problem, because the temperature of the universe is so high that atoms are, the electrons and atoms are pulled away from the atom because it's too hot to keep them on the atom. And so the universe doesn't contain atoms, it contains protons and electrons. Right? Light is electromagnetic radiation. Right? Because of which light interacts very strongly with charged particles. Protons and electrons are charged particles. So which means that if I have a light particle, a photon, or electromagnetic wave moving in this direction, inside this gas, this plasma of protons and electrons, it will go a short distance and immediately you will see an electron. And it will hit the electron and scatter off it and change its path. To change its path, you will see another electron, scatter off that, change its path. See another electron, scatter off that. So what will happen to a light beam, a light photon, is that it will go chuk, 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 all over the place. It will just keep scattering. It can't escape. It won't travel in one direction for much time. It will keep going chuk, 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 off things, scattering away. What this means is that light is trapped inside this plasma, inside the soup of charged particles. And that happens for a huge amount of time, 400,000 years of the universe, as long as the universe contains a plasma. Right? But now the universe is expanding. It's expanding slowly outwards, the temperature is dropping. And as the temperature drops, there comes a time, 380,000 years or 400,000 is written over here, when the temperature is low enough that you can have stable atoms. The proton and the electron can come together and form a hydrogen atom. And hydrogen atoms are neutral. They don't have a charge. Because proton has positive charge, electron has negative charge. When you move them together to a hydrogen atom, there's no charge. Electromagnetic radiation doesn't care about neutral particles. So the universe suddenly now has all these neutral particles because the temperature is low enough that you produced this neutral sea of particles. But now what happens to the radiation? Any ideas? So remember what I said. I said that the universe, think of the universe as a balloon. It's full and it's expanding outwards. It's full of these charged particles. Right? It expands outwards and these charged particles and radiation are inside this balloon. It's not a good picture, but it's okay for visualization. And the whole universe expanding outwards. At some point, because the temperature is dropping, the charged particles fall together and they form atoms. So now suddenly this universe is much bigger and you have a lot of atoms inside. Now what happens with radiation? Remember I said initially the photons going chuk 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 around the place. Right? They were hitting electrons and scattering. Now what happens? Any ideas? Yeah?
Now since all the particles there are neutral and dense, so the light are not no longer trapped and it can go into end to end in any direction.
In any direction. Is that in any direction or in a straight line?
In a straight.
Precisely. Bang on. What happens is that a photon now, as this universe is expanded, and you have all these particles which are now neutral, a photon which is going like this now is going to just keep going like this. A photon going like this will keep going like this. In every direction, there will be billions and billions of photons going away. They won't see the radiation, they won't see the hydrogen atoms at all. They basically go in straight lines. And that's a prediction of the Big Bang. Because again, it's happening for a very simple reason. It's just that the temperature has dropped. So at late times, the whole universe, when you look in any direction, it must be filled with radiation. With radiation which is coming from this epoch of what is called recombination. The recombination of a proton and an electron to produce a hydrogen atom. After that epoch, the radiation doesn't seem matter anymore. It just goes away. And so from every direction around us today, we should be seeing radiation from this epoch, which is called the epoch of recombination. That's what we see over here. That radiation is called the cosmic microwave background. It's called the cosmic microwave background because the radiation peaks at microwave frequencies. It's called cosmic, obviously, because it's coming from the Big Bang. It's a background because you see it in every direction. It's not coming from a galaxy or a star. It's coming from just after the Big Bang. And that radiation is a prediction. The existence of that radiation and its temperature is a prediction of the Big Bang cosmology. So remember, two things are predictions. One is nucleosynthesis, which happens right here, and then this radiation from 400,000 years after the Big Bang is predicted to be present in all directions. And I'll show you evidence for both of these. So after that, what happens? You want to go ahead? Yeah.
这边很重要啊，就是说大霹雳有发生，有两个，今天讲了两个重要的证据，就是说宇宙从一个很热的点开始，很小的。第一个就是nuclear synthesis， 有核的融合，就是用合成的方式，那很热的东西产生了两样东西，第一个就是产生4样东西，第一个是 deuterium 氘。氢的同位素，氦3 helium-3， 氦4 helium-4， 还有 deuterium 锂，还有那个 lithium。锂是周期表上的第3个元素，这几个元素都是氘啊、锂啊，都是核融合，也就是后来星球核融合很难产生的，所以只有靠一开始的时候的这个就大霹雳的那时候的核融合的产生。那氦4星球是可以产生的，可是我们宇宙没有老到可以产生那么多的氦4，所以一开始的时候，刚才讲了一个很重要的概念，就是一个好的科学理论，包括物理的学说，不光是可以解释现有的现象，它还要能够做预测。那大霹雳学说预测，就是说当时有这一很高温、极高温的产生了核融合呢，因此在宇宙各个地方，不管你往各种星系各个地方看，这4种东西的比例一定都要一样，因为当时宇宙产生了这个核融合，这是第一个。第二个就是刚刚讲的很重要的一个概念，原来刚开始都是电子啊、质子啊都是游离的，游离的东西光很容易被散射，散射以后就是一下子被往这个方向被反射，一下往这个地方反射，乱来乱去的散射。那么因此光是不透明的，很像我今天走在路上，这个尘土走来走去，尘土飞扬的话，光就不透明。可是要是尘土都下沉到地上的话，光线就透明。那一个 plasma 就是游离的东西了，就是不透明。可是，一旦宇宙冷却到一个什么地步呢？就是说这些原子都跟质子结合成原子的话，变成中性的粒子的时候，这时候光就透明。所以大霹雳的宇宙论预测，在宇宙从大霹雳开始以后，38万年，差不多40万年左右呢，这时候宇宙就应该膨胀到冷到那个地步。这时候宇宙变中性，它有一个字叫 recombination，recombination 就是电子跟原子核结合变成原子，中文叫复合，就复合成原子了以后，这时候是当时的这些光最后一次跟电子跟物质散射，最后一次散射发出来，光变透明了以后，我们看到就造成了宇宙微波背景辐射，也就是预测说宇宙应该有无所不在、到处不在、无所不在的这种辐射的这个预测。
So we said that microwave background radiation comes from this period about 400,000 years after the Big Bang. Again, this radiation has a prediction attached to it. It must be uniform. It must come from all directions with the same temperature. Right? So same temperature from this radiation, the same kind of radiation. I should look over here and see the same kind of radiation. It should be uniform across the sky. That's the picture that we had. I'll show you evidence for this in a short while. Now what happens? Now the universe contains hydrogen atoms, some helium atoms, 25%, and radiation. Radiation is going away. And then you have a period which lasts for about 400 million years, in which the universe just expands outwards slowly. And the universe these are called the dark ages. They call the dark ages because that's the period in which there are no stars, there are no galaxies. The universe is just slowly expanding outwards. Right? Because remember, we said at the start, at this period, the universe is all uniform. Somehow you need to go from this nice. Oh, sorry, I didn't know. I love using my hands. So somehow you have to go from this universe, which is lovely and uniform, to a universe today which is full of galaxies. And that process happens very slowly. It happens in this period, in what is called the Dark Ages, and I'll show you what actually happens in a short while. And so about 400 million years after the Big Bang, the first galaxies and stars form. That's the picture. That happens over here, and the universe is still expanding. First stars form here, small galaxies form here, and steadily, until finally big galaxies start to form somewhere over here, about 10 or 12 billion years ago. And then we get to today's universe with the usual galaxies that we know and love. And there's one interesting thing, which is that at some point, 7 or 8 billion years ago, the expansion starts to accelerate. So remember, if I have an expanding universe, the universe you would imagine, the acceleration would slow down, or rather the velocity would slow down. The universe is going to be doing work when it's pushing outwards against the gravity of the mass inside. And so it would be very surprising if the universe were to suddenly increase its speed. But we believe that's what's happening today. And that's shown over here by this accelerated expansion, which is due to, we think, something called dark energy. I'll tell you a little bit about that in a short while. So these are the epochs in the history of the universe. There's a very early universe, which I call the particle physics epoch, which is less than about 1 second. So less than 1 second after the Big Bang, the universe is full of these subatomic particles. Big Bang nucleosynthesis happened in the period roughly 1 second to about 20 minutes after the Big Bang. About 400,000 years after the Big Bang, there was an epoch of recombination, where protons and electrons merged together, formed hydrogen atoms, and that corresponds to a redshift of about 1100. So remember, higher and higher redshifts is earlier and earlier in the history of the universe. So 1100 is the epoch of recombination, and that's where we get the cosmic microwave background radiation from. And then for about a few 100 million years, there are no galaxies or stars, they're just hydrogen, helium, and radiation, and these are called the dark ages. And that goes on from roughly redshifts of 1100 to redshifts of 30, so about 400,000 years to about a few 100 million years. Galaxies start to form, the first big galaxies, at redshifts of about 100, 150, 200 million years. And they continue to form up to today, 13.7 billion years after the Big Bang. Roughly redshifts of 30 to today. The first stars switch on. Of course, that's part of galaxy formation. At about the same time, 100 million years ago, redshifts of 30. There's a very funny epoch that happens because we know today, look at galaxies. I said that, there was this epoch of recombination 400,000 years ago, in which protons and electrons merged and formed hydrogen atoms. So you'd imagine that space between galaxies will be full of hydrogen atoms today, neutral hydrogen atoms. And we know from observations, this is not the case. Space between galaxies is full of ionized gas, which means protons and electrons separately. It's not hydrogen atoms. So something in the history of the universe must have ionized the universe, must have re-ionized the universe. And that, we think, is done by the stars, these first early stars, and that's called the epoch of reionization. And it happens about 200 million years to about 900 million years after the Big Bang. Redshifts of 20 to about 6.5. And we have, again, evidence for this, direct evidence for this. And then finally, very late in the universe, the dark energy starts to dominate the universe, and the universe starts to accelerate outwards. So in all of this period, from here up to here, the universe is decelerating. The expansion is going slower and slower and slower. And that's because the energy density of the universe is dominated by matter or radiation. Radiation at very early times, matter at late times. But remember, when the universe expands, the matter density is falling. And it's falling like the volume. So if the universe doubles in volume, the density falls by a factor of 2. And so as the universe keeps expanding, the matter density keeps dropping until at some point we think about 8.5 billion years after the Big Bang, the matter density is sufficiently low that this funny thing called dark energy dominates the density. And then the universe starts to accelerate. I'll tell you what the dark energy is in a little while. So what are the two main pieces of evidence for the Big Bang cosmology? I said that nucleosynthesis. Remember, for cosmology, we need something that happens all over the universe. It should make a prediction, not that if I go and look at this galaxy, this will happen, but it should be everywhere, right? So the two big things are Big Bang nucleosynthesis and the cosmic microwave background. And the idea is very simple. In Big Bang cosmology, the light elements, deuterium, helium, and lithium, are predicted to have been formed within a few minutes after the Big Bang. So if that is correct, you expect uniform abundances of helium and deuterium in all galaxies, because they were all formed at that point. In fact, it's even more exciting than that. It turns out that for helium, you can actually predict the amount of helium that should happen, that should form, because the amount of helium that should form only depends on the relative number of neutrons and protons. So, at the time when helium was formed, after the Big Bang, all the neutrons, or most of the neutrons, went into helium. And so, all that determines the amount of helium is the neutron to proton ratio. So, you can actually predict how much helium there should be. And that was a prediction that was made, in fact, by Fred Hoyle. The other beautiful thing is that it's very hard to produce deuterium in stars. In fact, you can't. Because deuterium, it turns out, burns at very high temperatures. The only way we know to produce deuterium in the universe is after the Big Bang. So any deuterium you see in galaxies has to have come from the Big Bang. So if I measure the same amounts of deuterium everywhere, deuterium cannot be produced in stars. It has to be produced in the Big Bang. So deuterium is wonderful because there's no other known way to produce it. It's produced in the Big Bang, just after the Big Bang. The wonderful thing about both of these things, I'll talk about the microwave background in 2 minutes, is that they were both predicted by 2 or 3 people. Ralph Alford, George Gamow. Alford was Gamow's student, and Hermann. And all in 1948. Yeah?
So, can you explain the first star?
Yeah.
Newborn star?
Mm.
Or like the first star you say?
The first stars.
The first star?
Yeah. So that happens somewhere over here.
Yeah.
Yeah.
The first star.
Right. So these are going to be very different. These stars are going to be very different from today's stars. They form from neutral hydrogen directly. So what happens is that you have a galaxy. So you have the universe expanding, and you have these galaxies collapsing out from the expansion. And the stars form in these galaxies. So the density gets bigger and bigger and bigger. In fact, you'll see what happens in a little while. So let me hold on to that question for later. Because you'll see how galaxies form towards the end of the talk, and stars form inside those galaxies. So let's hold that question for a little while. So about 1948, 2 predictions came out. for the Big Bang, then you should be able to go and measure light elements everywhere in the universe, and you should see the same amount of helium and deuterium in different galaxies. And the second prediction, which is equally important, is that, as I said, at early times, the universe was so hot that atoms are broken up into protons and electrons. And because light is electromagnetic radiation, it interacts with the electrons and protons, with charged particles, and can't propagate. It kind of scatters off these particles. And once the universe gets cold enough, the protons and electrons merge together, form hydrogen atoms, and suddenly the light can escape and goes in straight lines. So the prediction from Alpha and Hermann and then Gamow separately is that we should see this light in all directions with a temperature of 5 Kelvin. That's a prediction for the Big Bang. Again, let me emphasize, this is a good theory makes predictions. You should be able to test a theory by its predictions. And the reason I think the Big Bang is a good theory is that it made both of these predictions. So let's look at the evidence and the real data. Oh, yeah.
刚才讲的有2样证据啊，是支持大霹雳。不过要强调一点是，这些学说这都是大的物理学家啊，他们在做理论的时候，1948年就已经预测，如果有大霹雳的话，会有这些原子核的比例会有微波背景辐射。他当年预测宇宙应该到处都有一个 K 的一个辐射，这在观测之前20年就预测到这个事情，所以这是才是重要的地方。所以他理论的预测远远大过。这张我稍微讲一点点，因为有很多的字啊。刚才那个老师也问了，这张是大概是今天就是说带回去宇宙的历史的一张图了。最早的时候，当然在1秒钟之前，大概都是一些基本粒子。现在在加速器里面要做的，或者是创造出来的这些基本粒子，都是在希望在重复这些事情。然后大概有一本书大家听过，叫《宇宙的最初3分钟》，就这个意思。前几分钟呢，就是把所有的一些基本元素就做出来，基本，后来的元素都是恒星做的。然后刚刚讲到这个 recombination， 就是在宇宙不透明的时期，那就是前38万年。然后即使已经透明的是光线，但是只有原子啊，还没有核融合点燃产生恒星，所以那段时间用历史上的黑暗时期来描述这个宇宙的时期。宇宙也有黑暗期，所以在38万年到1亿年这段时间呢，宇宙是黑的。后来才有了第一代的恒星，刚才老师也讲，他会再回答。然后第一代恒星出现了以后呢，恒星所发出来的辐射又把周围的气体给重新又游离。那刚才他提到的一件事情很重要，就是说我们用现在的望远镜回过时间去看，越远的东西越暗，所以我们需要越大的望远镜。可是越远的东西红移越多，所以星星的光线都红移到红外线去了。所以新的望远镜不但要大，而且要在红外线观测。所以新的一代的太空望远镜一定要是很好的红外望远镜，我们才能看到他刚刚讲他当研究生的时候，最大的红移的天体大概是4左右，现在看到最大的红移大概是8。新的一代的红外望远镜大概可以看到红移20、10几。换句话说，我们越看越早期的宇宙，有可能会看到这些最早的宇宙的时候的情形。
So these are 2 pieces of evidence for the Big Bang, the predictions of the Big Bang. If these 2 are right, there's a good chance the Big Bang model, at least, is broadly correct. If they are wrong, if you don't see them, the Big Bang is wrong. Guaranteed. You can't fix. In the Big Bang model, you must produce light elements a few minutes after the Big Bang, and you must produce microwave background radiation. It's very hard to get away from this. What's the evidence? So as I said, deuterium, 4 helium, 3 helium, lithium, predicted to be formed everywhere in the first few minutes. And the helium to hydrogen abundance, this ratio, 4 helium to hydrogen, only depends on the number of neutrons relative to the number of protons. So you can make a prediction, and this was made, that the amount of 4 helium by hydrogen should be about 25% by mass. You're sure of this? And the amount of deuterium, 3 helium and lithium compared to hydrogen, these values depend on the density at that time, because the higher the density, the faster the reactions to form these species. So they all depend on the density. So now I can go and measure the amount of deuterium compared to hydrogen, the amount of 4 helium compared to hydrogen, the amount of 3 helium compared to hydrogen by using spectroscopy of gas and galaxies. And the wonderful thing is that if the Big Bang is right, I have 2 clear predictions, well 3 clear predictions. The first prediction is that 4 helium by hydrogen should be 25% everywhere, all over. The second prediction is that all of these values, because they depend on the density, using the value that I measured, I can determine the density in the universe. And all of these should give me the same density, right? Because they all are happening at the same time. The density of the universe is the same when all of these are happening. So each of these measurements will give me a separate value of the density. And all the densities must agree. Otherwise, the Big Bang is wrong. You're sure? The third thing is that in every direction where I look here, look there, wherever I look, all of these actually the same values, because they're all produced early in the universe. All of these are predictions of the Big Bang. If any of these is wrong, the Big Bang is wrong. But this plot shows you the best data from today. And so what's plotted over here are the element abundances, which is D by H, 4He by H, all of these things over here, for the different species. So this is helium-4, this curve. This is deuterium, this is helium-3, and that's lithium. And this plot shows, theoretically, suppose the density of matter at that epoch was some value, how much would you expect to get for the element abundance? Right? So now I can go do a measurement of the element abundance, and I can simply put the point, for example, for deuterium, if I measure 10 to the minus 2 abundance, I'll put the point over here on this curve. And that means that the density of the universe was 10 to the minus 12. And so on. So from the measured abundance, I can put the points at different places in this curve. For example, if I measure a lithium abundance, a helium abundance of 10 to the minus 2, 0.01, I will put the point over here. On this curve, I'll put the point over here, and that will tell me that the baryon density must be 10 to the minus 12 again. The points over here, the measurements are here, the red circles. So the helium measurement, helium-4, is 25%. Bang on the prediction. 24-point-something%. Right there. The deuterium measurement is about 2.5 times 10 to the minus 5. Bang on here. The helium-3 measurement is here. And the lithium measurement is here. And what you see immediately is that for all of these values of helium, deuterium, 3 helium, lithium, they all fall exactly at the same density. They just match beautifully. Very, very hard to make this work. It's just wonderful. And I still, after 20 years of working in this field, I'm still amazed that such a simple prediction, just from very basic physics, actually works out. It's telling you something deep about the universe. What is even more beautiful is that you can actually measure the baryon density by a completely different method. which I will show you in a minute, but I'm going to jump to that right now. From the microwave background, it turns out I can measure the baryon density in the microwave background. And the density measured in the microwave background is this solid red line. It goes through every one of these points. So the density measured from the 4 light element abundances all agree. The density measured from the microwave background agrees with that. The helium abundance matches exactly what you expected. And in every direction, you actually measure the same values. It's just wonderful. It's amazing evidence. You know, if you could come up with a theory that could predict this kind of a thing, and it came out to be real, I would take my cap off to any of you. I would be proud if I could do such a thing. The tragedy, I should just go to the side a little bit. The tragedy is that George Gamow, who is one of the greatest scientists of the 20th century, did not get the Nobel Prize for this. That was because he was dead. He died early. Remember, this was predicted in 1948. These measurements were done in the 1970s. The first deuterium measurement happened in 1973. That's from this paper. The best measurements of deuterium were done in the late 1990s. There was still an argument in 1990 during my PhD as to what was the amount of deuterium. And that has been settled only about 7 or 8 years ago. So these predictions came from 1948. And 60 years later, they've been shown to be right. That's wonderful. It's just one of the most beautiful things in physics, I would say. So there's spectacular agreement between the density that you've inferred from the light element abundances and the completely independent microwave background estimates. So that's one of the great pillars of Big Bang cosmology. Nucleosynthesis fits beautifully.
这张实在是太漂亮了，所以不懂的人不知道到底漂亮在哪里，我稍微解释一下。就是这个当时做这个大霹雳理论的这3位人，他们预测说，刚刚讲这4个东西呢，要有一定的比例。所以第一个预测就是说，氦4跟氢的比例要是20%。那真正量到的果然是20%。那这个理论预测说，这个20%，这个25还是10这个比例呢，是跟当时发生这个核反应的时候，当时宇宙的密度是有关系的，对吧？当时宇宙的密度比较低的话呢，当时氦4除以氢呢就会比较低的比例，然后慢慢就饱和。所以这边就有好多氦4氘氦3等等。那后来测量氦4，宇宙中各个地方都是果然是20%。更进一步的是，量到了氘，量到了氦3，氘是到1973年左右才量，氦3锂等等，都发现他们所测量的值，所要求的宇宙当时发生这个核反应的密度，这4种元素居然都在同一个密度，这表示它们是同时发生的。我说这是一个很漂亮的一个结果。然后他把等一下要讲的东西先拿出来讲，从这张图之所以来自的地方，就是如果去测量宇宙微波背景辐射，也可以去估计这个宇宙当时的发出来的当时的密度，是这条红色这条线，所以这条红色这条线也通过这几个观测者，所以这是大霹雳学说的一个很大的胜利了，就是表示它是很成功的。
Let's move on to the second big prediction of the Big Bang, and that's the microwave background. So again, let's look back at what we expect. So after a recombination between protons and electrons, there were very few electrons left free in the universe. All the electrons were tied up in hydrogen atoms. And because of this, the radiation free streams, it just goes in a straight line away in every direction. And what Alford and Hermann and Gamow predicted in 1948 again is that this radiation should be visible as what is called black body radiation. Do you know what black body radiation is? Have you studied black body radiation? Okay. So the prediction is that this radiation should be visible as a black body in all directions with a temperature of about 5 Kelvin. The exact temperature was not clear. Some people were saying 10 Kelvin, 15 Kelvin, but definitely in every direction you should have the same temperature. The exact number will depend on the exact time that it happens after the Big Bang. But the temperature should be the same here and here and here and here. That's a clean prediction. And the wonderful thing was that 17 years later, Arno Penzias and Bob Wilson detected this radiation in 1965 with a temperature of 2.7 Kelvin in every direction. And that was the first evidence for a homogeneous and isotropic universe. Because remember, in 1965, the light element abundances had not been measured. This was the first tested prediction of the Big Bang model. That you saw 2.7 Kelvin in all directions. And this is a plot from a satellite that was sent up in 1992, the Cosmic Background Explorer. And they measured a microwave background temperature of 2.725 plus or minus 0.004 Kelvin in all directions. Today we know this number to 2.001. But what is even more beautiful is look at this curve. So these are the measurements of the intensity, how much light is coming from different directions as a function of frequency over here. And each point is a measurement. And what's been plotted, this black solid line, is a black body curve. And you can see the black body curve fits these points beautifully. It's just exactly on these points. What is even more beautiful is that any measurement that you make in science comes with some errors. You measure something, but it has some small errors on it. The errors on these points are roughly 1 upon 100 times smaller, 1/100 the size of the point. The errors are tiny on these measurements. And the black body curve fits this wonderfully. This is the best known black body in the universe. So it's amazing. This is another complete prediction. 17 years later they find it. 40 years later, 45 years later, they find this accuracy on this. And this, the microwave background radiation, is today our best probe of the universe. We can measure what the universe contains, how it evolves, by studying the microwave background. So I'm going to take a step back, because I said that the universe is completely homogeneous, completely, perfectly homogeneous, right? In every direction, I must see 2.7 Kelvin. But there's a problem. How do I go from a universe which is perfectly homogeneous to a universe which has billions of galaxies? We see billions of galaxies today. Where did they come from? If the universe was this nice, uniform gas 400,000 years after the Big Bang. And the answer is that about in the early 1970s, people realized, in the 60s actually, people realized the universe cannot be perfectly homogeneous. It has to be at least slightly homogeneous, very slightly. There has to be small perturbations, small places where the density is a little different from the neighboring place. If this does not happen, you cannot form galaxies. You're absolutely sure that the universe must be nearly perfectly homogeneous, but not perfectly homogeneous. That's a prediction again, which came from the Big Bang model, that the universe has to be almost perfectly homogeneous, slightly inhomogeneous. And now if the universe is slightly inhomogeneous, slightly non-uniform, this means that the microwave background will look slightly different in every direction. Very slightly different. By a tiny amount. And you know how much that amount should be from theory. That's another prediction of the Big Bang. The universe should be nearly perfectly homogeneous, but not exactly perfectly homogeneous. There should be anisotropies. If I look in different directions, the temperature should be slightly different. And these anisotropies are tracing these slight non-uniformities in the density. And the wonderful thing is that these anisotropies were first detected by the same satellite, the Cosmic Background Explorer, in 1992. And this was another thing which got the Nobel Prize. Both of these discoveries got the Nobel Prize. Let me show you what that looks like. That is a plot of the best map we have of the microwave background today. This, in fact, was just released a few months ago. It's from what is called the Planck satellite. And this is a funny plot. It's showing the whole universe in what is called a Moldede, an equal area projection. And I said that the universe is completely uniform, right? 2.7 Kelvin. So why is it that these points are all different? So these points are all showing different temperatures, red and blue. Red is higher temperature, blue is lower temperature. So why is it that it's different? The reason it's different is that a uniform component has been removed, has been subtracted. The uniform component is 2.7 Kelvin. Each point over here, the brightest point over here, is plus 200 microkelvin. 0.2 millikelvin. 10 raised to 4 times smaller than 2.7 Kelvin. The bluest point, the brightest blue point, is minus 200 microkelvin. Minus 0.2 millikelvin. So the scale on this plot is minus 0.2 millikelvin to plus 0.2 millikelvin. If I showed you the plot without removing the 2.7 Kelvin, you would never see any differences. It's just completely uniform. Because I've subtracted out, or somebody else has subtracted out the 2.7 Kelvin, now you can just about barely see these small inhomogeneities. So the anisotropies are tiny, they're 1 part in 10,000. But these anisotropies were predicted in the 1960s. You must have anisotropies of 1 part in 10,000 at least in order to form galaxies today. If you don't have such anisotropies, you cannot form galaxies. And that's for a reason we'll see in a minute. So today, the microwave background data are our best probe of cosmology. And our best cosmological model today, what is called the Lambda cold dark matter model, gives a beautiful fit to today's best data. So these are points showing the temperature fluctuations. Ignore the x-axis. This is highly technical. We can talk about this in more detail. But these are all the measurements from this image. Every point over here is the measurement. And the error bars are also shown. So the error bars are tiny on these points. And this green line over here is the fit of this model. And you can see that the fit of this model with the data are just wonderful. It's a spectacularly good fit. We know the cosmological parameters from this fit to about a few percent. And I'll talk about that later. But this is what we do in cosmology. It's one of the biggest things we do in cosmology today. We get spectacular measurements of the microwave background with these satellites, such as the Planck or WMAC or COBE satellite. Get more and more accurate measurements. And then we try to fit the best model to curves like this. And you constrain the parameters of the universe by fitting them to these data.
宇宙的背景辐射现在已经冷到2.7K 左右，所以它的辐射最强的地方是在微波。微波的话，地面上看不太到，所以都要到太空去，这都是太空望远镜的观测。几十年前呢是科比那个望远镜。那它有几种观测，第一种观测就是看看它的辐射呢在不同的波段强度的分别。所以在不同的波段，就是不同的波长强度的分布。那这个每一个点就是一个观测值，它的误差比这个点的那个大小还小了100倍，所以这个观测是非常非常准确的。观测值跟理论算出来的黑体辐射的黑体辐射就是完美的辐射值的吻合就非常非常漂亮。所以宇宙是一个完美的辐射体。它的温度就是2.725加减0.04倍，这是科比做的。那除了随着波长的变化呢，还做了一个观测，就是我往不同的方向去观测，看看温度有什么样的变化。那科比也做了，那 WMAP 也做了，那他现在做的是最新的，去年才释放出来的资料，是最新的人造卫星叫普兰克。普兰克也是把各个地方做出来的温度画出来，但是把刚才的平均值扣掉，还要扣很多了，要扣地球在那边运动还有太阳系银河系的贡献全部扣掉，扣掉以后就是宇宙当时的辐射。所以这张图是目前最新的进展。我们就发现宇宙比较热的地方。其实这是量的是温度，不过其实就是密度。宇宙密度高一点的地方、热一点的地方用红色的，冷一点的地方用蓝色的冷的颜色来表示。发现最高跟最低呢，只差了正负200个 microkelvin， 只有1/1000的上下起伏。是这一点点密度的高低起伏，造就了我们现在是发生什么样的事情。造成我们后来有这么大的结构的变化。那这一张图呢，就比较没有讲。这张图是这张图做它的角度的分析，发现角度越靠越近的，它们到底有多少成对的后来发现跟现在的所谓的暗物质，现在的宇宙论最新的宇宙论的参数去弥合的，包括暗能量有70%也是一样，观测值红色的点跟理论值是吻合的很好，才让天文学家有把握说当时或者是现在的宇宙的起源跟演化到底是用什么样的方式进行。
I should mention something else. The peaks in this curve are also a prediction, 1970, of the Big Bang cosmology. So these peaks were detected, this first peak was detected in the late 1990s, about 30 years after prediction. So again, I'm trying to emphasize that the Big Bang has actually made predictions for each one of these things, and every one has come out to be right, with observations done 30 years later. So much before the observations were done, there were actually predictions coming from the theory, and that's an example of a good theory. A good theory is something that says, go and look for this, and you will see this. And if you don't see this, I am wrong. And the Big Bang is a good theory. It's made these clean predictions. So now there's a big question mark. As I said that this universe is nice and homogeneous and isotropic. Very early times. And then you form galaxies. So the big question is, this universe was nearly perfectly homogeneous. As I said, to 1 part in 10 to the 4. Remember, these numbers are minus 200 microkelvin plus 200 microkelvin. The biggest anisotropy here is 0.2 Kelvin, 0.2 millikelvin, sorry. While the temperature is 2.7 Kelvin. So the anisotropies are 1 part in 10 to the 4. And we've gone from a universe like this, 400,000 years after the Big Bang, to a universe like this today,
This is the Hubble Deep Field, the deepest astronomical image that we have made so far. It's a wonderful image, made with the Hubble Space Telescope. And the universe, we can see clearly, is massively inhomogeneous today. There are